Hello everyone, welcome to this session about microservices and Internet of Things. So we're gonna talk about this agenda today. A little bit short about me. I was born in Spain and then I moved to Sweden around 99. The people in Spain have the capability to talk as much as the people in Osaka. I started with Java in 2002 and although I'm from Spain, I do not fight bulls. My connection with Japanese culture started in the 80s. So it was the golden time of Japanese culture in Spain. And a lot of culture in terms of manga, TV, and movies end up in Spain. And then this pushed me to read a lot of literature from Japan. And my favorite authors are Natsume Soseki and Kenzo. Well, let's get technical. So I don't know if you remember a couple of years ago, there was a hype about Internet of Things. They were promising connected homes, connected offices, all these kind of things. And well, in Europe and in US, nothing of this actually happened. So all the people are wondering what happened to the Internet of Things. And what it has happened is that factories get fully connected. So the difference between an old factory and a new one is that now when a car is produced, from the minute that the car gets a chassis, there are put 5 SIM cards. And the minute that the car starts being manufactured, the car producer gets live data from the car about all the different components. So this is just an image of where at the beginning, the people thought it's going to be 1 SIM card, but now there are up to 5 SIM cards in the cars. The other thing that changed was that now people try to manage devices that are common or simple remotely. So this allows you to scale much more. So Grundfos, a Danish company, they sell water pumps. And although they're based in Denmark, they have a lot of water pumps in the middle of the desert. And they can see in live data how the water pumps are, how much they should charge for those people or those companies, and when they have to actually replace it or do maintenance. So the difference is the following, that the reason why Internet of Things didn't pick up in the past is because the infrastructure is not ready for having those millions of SIM cards everywhere. And therefore, the new network that is coming, the 5G, is completely different than the 4G. So 4G is just an evolution of the 3G that allowed us to download more data. And the difference is that in the past right now we have around 6.5 billion devices connected. And we're going to move very quickly into having 20.8, meaning you're going to triple the amount of devices connected. So this requires that the 5G provide new features that we don't have in the 4G. And the most important thing is the virtualization of everything. So in the 4G network, it's very hard to provide virtual routers, virtual switches, this kind of hardware equipment. You still have to have it as a telecom operator. But now, thanks to 5G, you can provide all these devices virtually. The other part that is very important is to transition from old architectures to new architectures. And for that, the part that is critical is to provide partitioning. So partition is the key feature that allows us to maintain old systems and evolve them into new ones. The other critical part is going to be low latency. So the devices that are going to use are critical. So hospitals, stock markets, everything is going to go through the 5G. And then we need to provide under double digits milliseconds latency in order to provide those services through the telecom operator. And because everything is going to be connected, the security has to change as well. So that whatever device you have, it has to be really secure from cyber attacks or other mechanisms. Some additional features is, for example, the high speed. So it's very important that when you are in a high-speed train, you still can get the speeds provided by 5G or the latency of 5G. And this is something that 4G now cannot do. Also, because you're going to have, as I mentioned, billions of devices, it needs to be very energy saving compared to the past. And the other part is that 4G is very, very good coverage in cities, in large cities. But if you go to the countryside, then the speeds tend to go down. Here, going to be a shift on that, and is that you have to provide these speeds regardless where you are. So if you are in the countryside, in a mountain, or in a tunnel, you need to get those capabilities of the 5G. And from this like shift or change in the market, so Ericsson, a Swedish company, created a product called UCM. UCM stands for Universal Control Connectivity Management. And the question was like, okay, I'm Tesla, I am maybe Volvo as well, I may be like Siemens as a factory, and I have all these millions of SIM cards to manage. How can I manage all those SIM cards or devices? And the answer is through an API. So you create an API to manage all this equipment. And this have to rely on microservices architecture. They also, like, one important aspect when you have so many devices is scalability. And there where Kubernetes provide those orchestrations. So the project was created in 2017, like a startup. And we had a very small microservices. I know that in Japan, microservices are not still used, or like in the many of the JAX we have been to are still like far from adopting microservices. But actually, you can start as a developer doing it by yourself. So if you just take the whatever program you have and you put it in Docker, that's the first step to adopt microservices, to run whatever program you have already and try to put in Docker. I recommend to skip databases. So databases is a very challenging part to put inside Docker or into kind of any container technology. And also it's very easy to lose the data. So focus on, instead of like putting Java code or any code into Docker, that's a great first step. And the other part I recommend a lot is the entity control boundary pattern. So this is a very simple pattern, very old as well. This is from the 90s. That provides help to develop microservices. So imagine that we have like 3, 4, 5 microservices. So the boundary is the interface to the outside world, meaning other microservices. So when somebody wants to call our microservice, they will call the boundary. And then the boundary will delegate that call into the second layer, which is the controller. The controller will look at, can I solve this problem by myself? Or do I need to call other microservices? If I can solve it myself, it will delegate it into the entity layer. And the entity layer will collect data from database and return it. But if the controller cannot solve the entire request by themselves, it will delegate it to other microservices. So a little bit of like best practices or what we have learned from the past developing microservices. So if you go online, you're going to find millions of articles telling you that you should adopt microservices, and they are not very clear how you should get started. So this is a very basic introduction, like what choices you have to make when you start playing with microservices. The first one that is very important is to use a decomposition strategy. The second part is how the microservices are going to talk to each other. And this, believe it or not, is very old. This is as the unique processes almost. And also one of the critical part is actually deploying microservices. So the automation is very critical in deployments. And the last part, but not least, is actually testing microservices. So if you can't have a deterministic way to know if the service is going to work or not, then it's going to be very difficult to adopt any microservice architecture. The first point is the functional decomposition, and this is because we started with a greenfield. We didn't have any legacy code. We started from scratch. So then we cannot divide the architecture into like businesses or needs or something. So we have to start it by taking our assumptions and then break it into smaller parts. And this is like any other science, basically. So you take a big problem, you try to break it into small parts, and you try to solve it. So we started with this, basically. We have a browser or another microservice, and then we had a monolith. And this API, as I mentioned, is very simple. So we have three methods, basically, or 3 components: get device, change rating plans for data or voice or SMS, and then send an SMS to the device. and the database is outside the servers. So if we apply the functional decomposition to this monolith, we will break each function into a small service. We try to do one thing and do it very well. And then the other part that is critical is to avoid synchronous calls to other services. If you break all this and then at the end you do synchronization, what will happen is that you will, for example, try to change the rate plan for a device. So first you will call change rate plan, and then it will synchronously call get device, will fetch a device from the database, and then it will try to make the change it by sending the SMS to that device. And what will happen is that now you have blocked all the three services. So if another request comes to the server, until the SMS has been sent to the device, it cannot liberate any of those methods. So the last part that is very important is data isolation. So each microservice cannot share the database with any other service. Each service has to have its own database, and it can only be accessed through the API methods. And the result that you obtain is something like this. So you will have three independent services and three databases connected to each other. The benefits of this is that, for example, for large corporations, you speed up a lot of development. So the reason why Netflix adopted this technology is that they wanted to deliver much faster. They wanted to, if Amazon or any other competitor will launch a similar service, they could still stay ahead of anyone. And by doing this, basically each team in that service can work independently. They don't need to wait for releases. They don't need to wait for deployments. They have each of them its own life cycle. And the most important part with microservices is that when you have a big, large system, it's very easy to forget what provides value to the customer. So we said in this adoption that whatever service we have here, it has to be used by the customers. And if it doesn't provide value to the customer, then it gets dropped. We delete that service and we see how can we do it in a different way instead of using those code. As I said, it's very easy to, to couple all the services in synchronization. One very famous speaker, his name is Martin Thompson, he mentioned that synchronize is the cocaine of the IT science. And I agree with him. It's very easy to run into synchronizations or synchronize methods very easily. The other part that is very easy to forget once you have a very tiny database is actually the transactions. So many people, they think, oh, we have this simple service, we just store data here or JSON, and then they forget to implement transactions. And the services tend to crash. The services are like millions of services. So it's very important to keep the databases up to date and very efficient. The next topic is the inter-process communication. Anyone that has worked with Unix or any other services, they have stated this is an extremely old problem. So basically, it's like I stated before, you have two services at the synchronous call each other. And then once you do that, the entire system becomes brittle. So the most common case is to replicate data across all these services. And that tends to lead to distributed state. Distributed state is a very complex problem that many large companies like Netflix or Google have tried to solve. And up to date, they don't have any really good solution. And I don't think we're not going to come with, it's a very hard problem. I don't think anybody is going to solve. So what you have is trade-offs. You will have different type of trade-offs. And what we did is basically we replicate but very small portions of data. So we just take table rows and replicate it. And then this keeps the system going on to a certain limit. But this doesn't scale endless like many things. So the last part before testing I would like to talk is deploying microservices. So microservices only works if it's fully automated. So if your deployments at some point are manual or they rely on manual steps, it's never going to work. So if it's 3 o'clock in the morning and some services crash, the system has to redeploy new packages or new services automatically without any human intervention, regardless of the time or the day, or everything has to be fully automated. And there are different strategies for that. So basically, for when you start with microservices, you try to be efficient. So the first thing that all the people do is to do one multiple service instance per host. And this has advantages because it's very efficient and it's very fast. And at the beginning, it's very appealing. But when you move this into production, this tends to be a nightmare. Because the minute of one microservice crashes and you have a high load, then the JVM might crash as well. And then it will take down all the other services under that JVM. So this doesn't provide isolation, and it doesn't provide, it provides a shared JVM heap. So it's not so good. And what you could do, or what we are doing, is basically a service instance per container. It's not perfect either, but it provides you service isolation. So if a service crashes, you can just redeploy a new one, and it won't impact the other services. The good part with this one is thanks to Docker. If you have the Docker registry, you can provide very quickly a startup. And the problem is that the trade-off is that it becomes very complex to administer. So you need a Kubernetes expert in your organization, somebody who knows Kubernetes from top to down. And also there's a security aspect of this, and it's that all the services will share the kernel. And that could lead to security problems if you don't keep the operating system up to date. So the last topic for now, once you get all this started, then the key question is how to test. And what we notice when we try to test is the following. The classic approach that is sold in many books doesn't work. It doesn't scale. It doesn't provide the correct feedback to us. And we struggled for some time trying to figure out how we could do different. And then I attended a talk from a person called Asaf Mesika, and he did a transformation in our organization in Israel where a company changed into what did they call it, diamond approach. And this diamond approach is very efficient because they focus on what the customer obtains from the microservices. So the unit test becomes very small. They just focus on key part. Forget about having 100% test coverage. It's completely useless. Then they increase a lot the component test, how you different components are put together, how they work together. And the most critical part of this is actually the integration test. So the integration test will tell you if your system is going to work or not, and how well it's gonna work with different components of different services. And the critical part is actually the end-to-end test. So this is kind of like your life insurance. Is the customer gonna suffer anything? Is only the end-to-end test who can provide you this information. How much time is left? 5 minutes? I think I will take questions if you have any. No? Anyone that is using Docker, microservices? You don't count. What Java version are you using, or what programming language are you using?
Java.
You can do microservices with any programming language, with Python, with Go, with anything. So this is more like a speed up. If you try to beat up competitors, then microservices is very scalable. The other impact that microservice has is actually on the cost, because you only use the services when you need them. So this can lead that the next architecture is called the Lambda. And basically you have functions that are called only on demand. And the rest of the time doesn't cost you anything. So it's a big difference having like a lot of servers or a lot of hardware where you have a lot of software deployed, and it costs regardless if the people use it or not. Well, then thank you very much. Pleasure to be here.